Welcome to our weekly theoretical computer science seminar at Jagiellonian. Today, Jakub Kozik is going to tell us how many hyperedges in a hypergraph you need to have to force three columns, right?
Yes.
In a deterministic way.
Yes.
Okay, the floor is yours.
Okay. So I'm glad to see you here. And so let's start. We are going to deal with hypergraph coloring. And just to settle things and not to look too wide, we fix a size of edges. All right. For today's talk, we consider hypergraphs in which every edges has the same size. Okay, so this kind of hypergraphs are called K-uniform hypergraphs when the size of edge is K, or K-graphs for short. You can see in the picture an example, such a structure. And it turns out that two coloring of such creatures is already interesting and hard. So we are going to deal only with two colorings. And that two coloring of hypergraph is proper if no edge is monochromatic. It is a well-respected definition. So in 60s, Erdős and Heinal, they asked the question, what's the minimum number of edges in a K graph that cannot be two colored, that needs at least three colors? And this function is denoted by M of K, and in some sense, it is a central point of today's talk. So what do we know about this number? We have two bounds, and in some sense, they are close to each other. So the lower bound proved by Radhakrishnan and Srinivasan after a few improvements over the naive bound looks like this. So it's the factor 2 to the k, which will be on every slide today, and some polynomial factor, which is roughly square root of k. K is size of edge. All right, and we have upper bound, which is the same, 2 to the k, right? And now polynomial factor is k squared. And this is the best that we know, and as you can see, it has not been improved for quite some time. In particular, this lower bound, it was just the first non-naive lower bound that was obtained, and for over 50 years there is no improvement. So you may think that there is a reason that there is no improvement, because these two bounds are already quite close to each other. And I don't see it this way, and I'm not the only one. So I've heard, or maybe I've read some time ago, a comment on this by Joel Spencer, who said that in this probabilistic framework is, or in case of hypergraph coloring, this to the k, it serves as, it can be considered as a unit. So you can pretend for a moment that you don't see it here. Just square root of k and k squared. Now the gap is much larger, and if you want some more convincing arguments to look at this or to look at this in this way, there are some alternative definitions. So instead of asking what's the minimum number of edges, you can ask how large can be the expected number of edges, of monochromatic edges in a random coloring of vertices. And the second statement, it's more robust in a sense that it well generalizes to other cases. So for example, when you have many sizes of edges. All right. So I've worked a lot on improving these bounds, and you can see that I failed so far. But out of these two, the first one might seem pretty small, slightly more involved, but at the same time, it might be more easier to improve. So this one is more frustrating. The upper bound from 64. The proof of this bound is, from our today's perspective, it's quite simple and naive. So what Erdős proposed, and it was like one of the first successes of the probabilistic method, was just to take a specific number of vertices and put this number of random edges, and then one can show that with high probability, this hypergraph cannot be two-colored, right? So means that such hypergraph exists. Okay. This number of vertices, k²/2, it's interesting because, okay, simple answer would be, if you want to get a good bound, just take a random hypergraph, right? But random hypergraph is not precisely defined. So first, it is random in the sense that every edge is uniformly sampled. Okay, but the second thing that we need to fix is the number of vertices, and clearly we have some space there for optimization. And it is intuitive that you want small number of edges. Probably it's you want rather small than very large number of edges, but it cannot get much smaller than k². And if you take a look at this proof, there is a point then it is assumed that the number of edges is at least quadratic, just for some estimation to hold and for the proof to go smoothly. But it turns out that it is not just convenience, and there is a reason to think that the number of edges should be quadratic. Excuse me, vertices, sure, of course. Where the number of vertices should be quadratic, and this is just because if you can show that if the number of edges is like of vertices is like k²/log with some coefficient here, then you can improve a lower bound. And if this coefficient is like 4 or 8, this lower bound goes already above k². So it's not only that there are no random hypergraphs with this number of edges that are not two-colorable. With this number of vertices and small number of edges, there are just none. Okay, when it comes to random hypergraphs, this proof is rather basic. There's just a little bit of technicalities in there. So you may think that it's not accurate. Okay, it's easy to show that at this point the hypergraph is not two-colorable, but maybe it stops being two-colorable slightly earlier. That's also not true. So we know these days that this specific value alpha, I didn't put it here, but it is known. It involves the Euler constant. It works as a threshold. So when the number of edges is smaller, then random hypergraph is with high probability two-colorable, and if it goes up higher, it stops being two-colorable with high probability. Okay, so number of vertices is an interesting additional features of the constructions that we are going to look at. So let us just note it. And number of vertices in this random construction is like k². I write here k²/2 for a reason. It doesn't really matter if, I mean, I didn't write this constant here specific, so I can change this constant here and it will be hidden. But k²/2 is suspiciously similar to k/2. And there might be some reason for this. So this tiny observation, you can delve into it, and you can see that in fact this what this construction gives, it can be interpreted in some sense, in some Ramsey style. Okay, so instead of see, the number of vertices looks like a number of edges in a clique of k vertices, right? So an edge of this hypergraph can be interpreted as a subgraph of this clique with k edges, and this property that in every color you have one edge monochromatic. It just says that one of these hypergraphs, one of these graphs will be monochromatic. Okay. So we have this upper bound, which is quite old, which is quite simple, and it was quite challenging and frustrating to improve it. As I said before, I failed so far. But one way of trying to understand what happens and what can be improved is to look for similar problems. And the similar problem that I think is quite relevant is our deterministic construction. So we have randomness here, and this randomness, it obfuscates everything that happens underneath. So what can we say if we just don't allow random bits in the construction? So this is the main topic. Okay, I just rewrote here this this bound to put the other bounds in the same shape. Okay, so the first bound given by Erdős and Heinau in I don't know, 60s or 50s. It's hard to say it's a result. It's just an observation, right? That if you take just 2k minus 1 vertices and make an edge of every k subset of this set, and this hypergraph is not monochromatic, it gives roughly 4 to the k edges. So the number is huge compared to what is necessary. But still, I suppose that the reason for this was just to show that this function is well defined, to get some upper bound. This upper bound has an interesting property that the number of vertices is very small, right? So it's minimum number of vertices, 2k minus 1. Okay, let's not spend too much time on this observation. In 64, in the same year in which Erdős published his construction, Abbott and Moser came up with deterministic construction, which gave a bound like this, totally like 65 to the k. It is, I would refer to this as a recursive construction, and I can draw a picture how it goes. So the idea was to if you have two hypergraphs that are not two colorable, you can build from them another one which have larger edges and still is not two colorable. So it's it works like this. We have hypergraph HA with edges of size A, E, and hypergraph HB with edges of size B. Okay. So what do we do? This formula shall lead us. So for every for every vertex of HA, we put a copy of HB. So we start with a bunch of copies of HB. Okay, it's just independent and disjoint. Okay, and now for every edge of HI, suppose that we have edge like this. I use some color. If we have edge like this in HA, we take one edge from here, one edge from here, and one edge from here in every possible way. And we construct in this way an edge of our new hypergraph, right? So this is one choice. This is one edge. Okay, this is another. It is supposed to be green. And so on. Right, this is the construction. So what is the size of new edges? So we have in HA, this edge has like A vertices. Okay, but every vertex now is in fact as large as the edges in HB. So the new size of edges are H times B. And if you want to show that it's not too colorable, that's an easy exercise. I will leave it to you. Okay. So they came up with this construction. And now, once you have construction, you can try to apply it for some numbers. And actually, to obtain this band, they used numbers which are powers of 3. So a small number of k, the values of n is known. And for k equal 3, this number is exceptional. It is 7. Because of very simple example, which is quite misleading. And for some time I used it in my talks, but I think it's just a bad example. 7 is exceptional because it's smaller than 2 to the k, right? So it's just because 3 is too small for things to happen. But in this recursive construction, you can benefit from it. So you can apply this for 3 to the power, and then apply this recursion, and you will get something like this, square root over 7. Actually, for the powers of 3, you don't even get this O of 1. Okay? This O of 1 is just to fill the gaps between these powers. Okay, this was the story. And now, many years later, Heidi Gebauer came up with a beautiful and simple construction that improved this lower bound to the value which has the right exponent, 2 to the k. In some sense, I think it was unexpected. Okay? In many other cases of Ramsey theory, you just don't have the deterministic constructions that are this close to the optimal. Okay, now this construction. Oh, what about number of vertices? I said in the naive bound we have like 2k vertices. In Erdős probabilistic bound we have like k square. Here, number of vertices is exponential. That's just by this construction. And in the Gebauer construction, it is also exponential. So, and in the improvement that I'm going to present, it's also still exponential. So it's quite interesting it's quite interesting feature, okay, which can say something about your construction. Can it be realized with smaller number of vertices? So the improvement will be, of course, this lower order term in the exponent. Right? We cannot go below 2 to k. You may think it's not much, and I agree, it's not much, but in some sense, it complements the work of the powers and push this construction closer to its limit. All right. So let's start with recalling the Gebauer's construction. It is convenient to organize vertex set of the hypergraph in a rectangular array. Okay, so we have S rows and 2t minus 1 columns and S rows. maybe I should write some values for these parameters just to keep you to help you think about them. So t will be roughly k to some power, like let's say 1/3. Okay, so t is smaller than k, it is like cubic root. Okay, and s is much larger. Something like k over t times 2 to the t. 2 to the t, right? It's dominating factor here. So it's exponential, okay. Okay, so this already says what would be the number of vertices, and you can see it's exponential. What do we do next? Okay, we are going to just every cell of this array to represent a vertex, and we are going to color these vertices red or blue. And if we are going to deal with some subsets of rows, and the sets of rows which will be interesting to us will have the property that in a specific coloring there one of the colors is dominating. Okay, so we have a row, and this row has more red vertices than blue vertices. We'll say it is mostly red. And the construction, it goes in 3 steps or 3 phases. In each phase, in the construction, some decision is made. Okay, so in the first phase, we decide with which set of rows we are going to work. Okay, so we choose t of rows over from the 2 t minus 1 rows. You can recognize this formula from before. Okay, so this formula on the right, it just shows the number of choices we have in the consecutive phases. So in the first phase, we have this number of choices to choose the set of rows that we are going to work with. Okay, in the second phase, we apply some cyclic shifts to rows. Okay, so every chosen row is cyclically shifted by some numbers. Okay, and we have all the choices of all we can choose any time any sequence of shifts. Okay, so the number of choices is s to the t. We have t rows, and every one can be shifted by s. And in the final phase, we choose k over t columns, and from the vertices of these columns, we build an edge. Okay. So we have 3 phases. In every phase, we can decision. So we can think of making this decision in every possible way, and in every sequence of decision leads to some edge, and all these edges are put into the edge set of our hypergraph. So the construction is quite basic. We can quickly check that it is really k uniform. Okay, we have k over t columns, and columns are we have t rows. Okay, so it really sums up to k. So we get some hypergraph, k uniform, but so nothing fancy yet. But it is surprising that it is not too colorable. How can we show it? Well, it's not yet true. It depends on our parameters. So an important decision we have to do is to choose S not too small. Okay, and this not too small is this value, and you will see shortly why. So we choose S to be this. That's exactly what I wrote here. Okay, so we choose S to be this value, and now it really becomes not too colorable. Why is that? So let's imagine that the vertices are colored. Okay, so every edge has some colors in it, and every edge is either mostly blue or mostly red, or actually it can be mostly both, but that doesn't matter. What's important is that there is a set of T rows in which the same color is dominating in every row. Okay, and we will take a look at this decision that chose these rows to work with in the subsequent phase. Okay, so we work in phase 2, and we imagine that every row is dominated. In every row, red is the dominating color. Okay, now the argument is that we want to show that there is some choice of the cyclic shifts in which K/T columns are going to be monochromatic. And this is quite obvious because if we choose these shifts randomly, then the expected number of monochromatic columns is exactly K/T. It's just because S is this value, right? So the probability that one column is monochromatic is like 1/2 minus 1. Okay, so it was in fact stated in this way in the Gebauer's paper, but just not to lose intuition, note that this I said about random shifts, but it is just an argument. The procedure just took every shift. Okay, so if there exists one, it will be found and it will be used to construct an edge. This edge would be monochromatic. Okay. Again, so we need S of at least this size, this value for sufficiently large number of monochromatic columns to observe. But you may think of doesn't pay to get S larger than that. Okay, so now we can observe that T is still not fixed, right? T can be anything. So now it's time to optimize T. So we just calculate what happens, and it's not very important. It's just boring calculation. But you get something like this, and colors shows what these factors, where these factors come from. So this factor that we expect 2 to the k, 2 to the k, right? This one, it goes from the choices of columns. But also, these choices of columns introduce another factor here. Okay, now if we want to choose T, you would like to see what are the most important parts of this exponent, right? And you can quickly see that this one is the most important one, and this one. So the best T that you can think of is the one that balances those two influences, and that's why T or to cubic root of k is roughly the best that you can think of. Okay, so you just take T of this order and plug it into this formula, and you get the Gebauer's result. 2 to the k times this k2 over 3, right? Cubic root to the power of 2. Okay, so this is very basic, very simple, and there should be much space for improvement here. And for example, you can easily see one place when you can improve. This is this first phase. Every choice of T rows, because this number of choices as, and as I said before, it looks like the naive it is in fact this naive construction. Okay, so we already know, we already have better construction. We can use, instead of this every choice of 2 rows, we can use here some recursive construction, or we can use this construction of Moser and Abbott. We can even use recursively Gebauer's construction to get something better. And the outcome would be not much better, because you can fight for crossing this 2 from here. Even if you cross it, it's not much. Right? Still, the dominating terms would be the ones I underlined before. Okay, so it's easy to improve in this first phase, but the improvement wouldn't be significant. So we have to look deeper. Okay, this is a repeated argument that there is a number of columns that if you choose shift randomly, there is a k over t monochromatic columns on the expectation. Okay, so it looks like an overkill, okay? Because we need just one sequence of shifts, which is good, but this argument, it doesn't show directly, but it seems to suggest that quite a number of these shifts would be good. Okay, so sequence of shift is good if the shifted array has k over t red columns. Okay, so desired number of columns. So exactly what we expect, at least. Okay. Right, here is the argument I said before. So there exists a good shift sequence. Now, there might be more than one good shift sequence. So just to trying to find it, let's generalize this property of being good to prefixes. Okay, so we can start with this array, and we choose. So first few shifts has been chosen. And so far we are good. We have a large number, like close to the expected one, number of monochromatic columns, monochromatic red columns. Okay, so okay, so this is good. Good shift is the good prefix of shift sequences is a prefix in which the number of monochromatic red columns is just at least the expectation. Okay, and now we can suppose that we have such a good shift sequence, and how many shifts are good to extend it. So we have some choices for the next one, right? In some of them, the number of red columns are more than half what we had before, and in some of them maybe not. So this is a good question. If we have a good sequence, in how many ways we can extend it? So intuition says that half of the choices are good. And indeed, it is true if this row is colored randomly. Right? If the row is colored randomly, then half of the choices are good. But it's not true. In the pessimistic case, it doesn't have to hold. So, but something quite close is true. So although not half of choices are good, we have some control over it. And just a large fraction of the choices are almost good. So almost good means that we lose half of the columns and maybe something more, a little bit more, but not much. Okay, and if we allow to lose a little bit much, then this number of good sequences is of good candidates for the next shift is large. Large means some constant. Okay, so we relax this definition, and it's instead of saying that sequence of shifts is good, we say it is epsilon good. So instead of cutting by half each time we add on a next shift, we allow reducing it by 1 minus epsilon. Okay, and okay, so we are going to lose something, right? Because now every next step, every choice of the next shift, it reduces the number of columns a bit more. So it's good point to see how much do we lose doing this. So previously we started with the value of S, which was chosen in such a way that after all the yes, we started with k over t, 2 to the t. Yes, and in choice of every shift, reduced this exponent by 1, 1, 2, 3, and so on. Right. So in the end, we have k over t. Actually, times 2, but I don't want to write -1 everywhere here. So we wanted in the end k over t columns, and it's still what we want, but now we don't lose. We lose a little bit more. So it's enough to start with this number. So we multiplying s by e is just enough, right? It's just because and choosing epsilon 1 over t. Okay, because 1 over t. No, this is additional factor that we lose in the whole process, right? So it behaves like e. So if we start with more columns, it is still okay. And in the end, we have k over t for the chromatic columns. Okay, so we established some. No, we didn't. We just stated some definitions. Yes, that instead of looking for good sequences, it is enough to look for epsilon good sequences. And yes, we will have to extend this length of the rows a little bit, but it doesn't hurt much in the end. Okay, so now we are going to see, is it true that there are many epsilon good sequences? And it turns out to be true. There are really many epsilon good sequences, and that allows to plug here a random argument. Very much like this argument of in technical details, it's very much like the argument of Erdős with this random construction. So using analogous argument, you can show that if we consider epsilon good sequences, then there is a large number of such. I will comment on this shortly. And if there is a large number of such, then a random choice would be so there exists a set of shift sequences of relatively small size, such that for every consistently dominating coloring of the array, at least one element of S is epsilon good. Okay, so in other words, it is a heating set for the set of epsilon good shifts for coloring. And the argument is the probabilistic argument is very basic behind this. What it would give. So previously we used the set of all shifts, and it gave a factor like 2 t squared. You may remember that t squared was one of its dominating summand in the exponent. And now if we can use instead this small heating set, we would reduce this 2 to the t squared to 2 to t times log. And then we optimize different function, and it can be optimized better. We would get result like this. That is the desired result. That is the claimed result. Okay, so at least it shows that it's possible. There are some small heating sets. So the trick is now to find them without random construction. Okay. We need some tools. And tools were prepared for the framework of combinatorial rectangles. So maybe I will show some names. Linia, Lube, Sachs, and Zuckerman. Yes, they work on this problem. They had sequences. Right, they work on sequences of length d, of numbers from 1 to n. Okay, and in such set of sequences, a combinatorial rectangle is just a Cartesian product of some subsets. All right. For such a rectangle, we can define its volume, like here, in a very natural way. It's normalized, right? So the whole space has volume 1, and some rectangles has appropriate volumes. And again, the same argument can be used to show that if we want a heating set for every set of rectangles of sufficiently large volume, then we can use random construction and we will get some quite small heatings. Yes, but they were interested in construction, a constructive approach, and they proved something like this. For some constants, there exists a heating set, subset of m to the d, of heating set of this number of sequences that hits every combinatorial rectangle of volume at least v, right? This number which is here. How to see that it's not large? And you can see that n, right? This possible choice of numbers is just in power 1 here. Yes, the remaining thing is 2 to the d, and d is some. Oh, d is here. Oh, okay. Maybe just if you just want to take everything, you would compare yourself to m to the d, and you have m to the 1 and 2 to the d. Okay. How did they do this? It's maybe it's more interesting how it happened instead of just using it as a black box. So it is construction based on expanders. So in fact, this this set of sequences that they promise they can construct, is just built this way. Then we take an expander, and we are going to take some walks in this expander. So this n, the expander of n vertices, and regular with some small number of small values. Okay, so this number n is just the possible ways of starting our walks. Okay, so we can start a walk in any vertex, and then we are walking through edges in every possible way. Okay, this is how we construct the sequences. But there is one more detail. It's not our walks are going to be longer. So we are going to we want sequences of size d. So we take walks. No, they took walks of like d times log. They took walks, and then from every such walk, they took first vertex and a vertex which is not far, the logarithm of n or something. Oh, no, it's related to this volume, right? It should be. Right, so this log v happens here. So they take this walks, yes, and they take a first vertex and the next vertex that is not too far, and the third vertex that is not too far, and so on. Okay, and that happens to work. Of course, you need to have expander, but there are some expanders, and there were already known some combinatorial constructions. They use a good example is Margulis expander here. Okay, so we can try to pretend for a moment that our epsilon good sequences are combinatorial rectangle, right? I told you before that the number of these epsilon good sequences is large. And if we express it in terms of volume, defined like here, the volume would be at least like this. For a fixed coloring, the volume of the set of epsilon good sequences is at least this one. Right? So, so if it happens that that these epsilon good sequences form combinatorial rectangles, that we are aiming to hit combinatorial rectangles of this size. Okay, and then they say that it's possible with this number of sequences. So it translates to this number of sequences in our construction. So it is pretty good. There are some difference in the constant here, but you can see t log t, just like in the random construction. Yes, so we are not that far away. As in particular, we are much better than what was used before, like t squared. So that's this improvement. But unfortunately, it's not true. So epsilon good sequences does not form combinatorial rectangle. Maybe they can in some very, very specific colorings, but in general, they don't. So this result cannot be directly applied. But for some time, I thought that maybe you cannot apply the results, but you can apply the proof, right? Maybe it's even, maybe it works even better because these epsilon good sequences are somehow more evenly spread in this expander graph. It's of course completely wrong. I mean, it's crucial in the proof that it is combinatorial rectangles, and for every coordinate you have a specific set of vertices in this expander graph that you want to hit. And if it depends on previous values, it's just rows apart. So not that easy. No, not that hard. It happens to be easy, but in some other way. Okay, so the idea to overcome this problem is first not to look at the sequence of shifts, but to look at the tree of shifts. So we have some many ways of representing this shift between these rows. And for example, it is clear that we are not interested in absolute shifts, but in a relative one. Okay, so for example, when we are discussing in how many ways we can choose the next shift to not to kill too many monochromatic columns, it's clear that it doesn't matter for us where these columns are or how they are shifted cyclically. So relative shifts are what matters. So we are going to work with relative shifts, and okay. So another consequence of this observation is that it was also redundant in a sense that, in fact, every edge was constructed in many ways. So because it is relative shifts what matters, so we can assume that the first shift just doesn't shift anything, right? That doesn't make any important difference in the result, but just clears some situation here. So let's imagine that we are dealing with shifts, and we fix the first shift to be 0, and then we are going to work with relative shifts, and we are going to represent them as a tree. So we assume that for simplicity, that this t is a power of 2, just for our trees to be nice balanced. Okay, and we are going to represent this sequence of shifts in this tree by some relative shifts. So this value here, it corresponds to the relative shifts between row 1 and row 2. Okay, this corresponds to the relative shift between row 3 and row 4, and so on. Right, this point between this and this, between this and this. Okay, and we go to the next layer. It's R23. It represents the relative shifts between those two shifted rows and those two shifted rows. There is still some space for how do you define it, but it doesn't really matter. Okay, so instead of writing these shifts in a sequence like this, we can imagine equivalently a binary tree and write this relative shifts. Or the sequence of shifts can be read from this tree and the other way around, of course. Okay, and now we have to move our definition from the sequence word to the tree word. So previously it was that shifts 1, 2, 3 was good if there were sufficiently large number of monochromatic columns, right? Now we say that relative shifts of level J is epsilon good if this one is good and this one is good already. It means that in those shifted sub arrays there is a large number of monochromatic columns. Okay, and this last shift is also good if it doesn't kill too many monochromatic columns. Okay, and too many is just what we aimed for before, 1 minus epsilon over 2. So this is the fraction of breadcrumbs that we can afford to kill, not more. All right, what did we gain? We gained the thing that if we consider one column like this, on level of the tree, these numbers are independent of each other. So whether this number is good depends only on first and second row. Whether this number is good depends only on the third and fourth row, right? And the sets of rows are disjoint. So it means that good sequences for level 1 form a combinatorial rectangle. And since it forms combinatorial rectangle, we can use this result of linear Zuckerman without even noticing that there are some works on expander underneath. Okay, and the same can be applied to the second level. So we apply again then the result and every consecutive levels. Okay, so we get small heating set for level 1. Okay. We have small heating set for level 1. We have small heating set for level 2. We have small heating set for level 3, and so on. And if we take a Cartesian product of all this small heating set, we will get small heating set for a family of epsilon good assignments of relative shifts. So the last thing to do is to calculate, and I will not bore you with this, but you can imagine that we have just logarithmic number of layers. Yes, here, and everyone behaves like roughly like very closely to this probabilistic argument. So looking at from this distance, it looks like we just get something which is close to this probabilistic argument, but losing a factor of log, which is still not much. But actually, some things cancel out in this calculation, and we don't even lose this log. So it's still t log t in the end. So what we did, we start with Gebauer construction, which used every choice of rows, every choice of sequence, and every choice of k/2 columns, and we managed to reduce this number of choices. So now we choose some carefully chosen set of sequences of shifts. Actually, we choose it in a relative way, but it can be translated. Okay, how does it influence the result? So instead of s to the t here, we get t to the t. And s is just a factor, so it is not important here. And we can once again optimize. Okay, we paid something, so we need to increase s multiplying by e. But this is a small price; it doesn't matter in the final results. And now, if we write this formula in this exponent notation, we can see that now the most important factor summands are this t log t and k/t log e. Previously, we have t squared here, right? So this two has to balance out, and that's exactly why we choose t square root of k over log or times log, something like this, right? Okay, so the number of edges becomes like this. We reduce it from 2 to the third to this one. Okay, so final comment or comment. I started that we can easily improve this construction by improving this part, not choosing everything, but something else, but doing some smarter way. And I said after that in fact, it influenced only this part, and it is not essential in the end. It vanishes because there are more important summands. But now take a look at this. More important summands are quite close to the t. We have t log t here, right? So if we can get rid of this logarithm, this would start to matter. So that's what I meant, that this original construction, it was unbalanced. It has 3 phases and 1 phase was irrelevant. Okay, it is still irrelevant, but it is very close to be relevant. So I believe that with some technical effort, maybe you can get rid of this logarithm from here. And then this construction gets balanced. And in order to improve it, you have to work really hard or come up with some different approach. Okay, I'm not sure if it's worth an effort to remove this logarithm, but improving this construction is worth an effort, especially that this original one was very simple and easy. Okay, I think that's all for today. Thank you.